A ghostly whisper from the very dawn of time permeates the cosmos. It is not the famous first light of the universe, but something far older and more elusive. This is the cosmic neutrino background, the faint echo of creation itself, a relic born in the first second after the Big Bang. By the end of this journey, you will know the 25 profound secrets this ancient signal holds about the fundamental nature of reality. We will confront why it is nearly impossible to catch and how it might reveal the true identity of dark matter. What invisible force from the beginning of everything are you most curious to understand? These particles are the ultimate cosmic escape artists. Born in a frantic blur of creation just 1 second after the universe began, they have not stopped moving since. For over 13 billion years, they have streamed across the cosmos, a silent, unstoppable tide. But time and expansion have taken their toll. The universe has stretched, and in doing so, it has stretched the very energy of these ancient neutrinos, cooling them to a temperature just a single degree above absolute zero. This is why catching one is perhaps the hardest task in all of modern physics. They are so feeble, so low in energy, that they barely acknowledge the existence of matter. 1 trillion of these ghostly particles pass through your body every single second, flying straight through the Earth as if it were empty space. This presents a technological nightmare. How do you build a detector for something that refuses to be detected? You cannot simply put out a net. The very laws of physics seem to conspire against the hunt. To capture just a single, verified relic neutrino from the Big Bang would be a feat so monumental it would instantly crown a Nobel Prize. It is the scientific equivalent of trying to hear a single, specific whisper in the middle of a Category 5 hurricane. The signal is unimaginably faint, buried under a roar of modern interference and countless other particles. This is the first and most fundamental mystery, a challenge that defines the field. What kind of brilliant machine could possibly listen for that whisper? This predicted temperature is not just a number on a cosmic thermostat. It is a profound echo of the universe's earliest moments, a fossilized record of how everything stretched and cooled. We know the cosmic microwave background, the first light, glows at a steady 2.725 Kelvin. The neutrino background is calculated to be colder at 1.95 Kelvin. This difference is not an accident. It is a direct consequence of the universe's expansion history, a cosmic clock that tells us precisely when these relics decoupled from the primordial soup. The exact temperature is a window into the number of neutrino species that flooded the young cosmos. Our models, built over decades, predict 3. But what if our measurement, when we finally achieve it, tells a different story? A deviation, even a tiny one, would send shockwaves through physics. It could mean there were more than 3 types of neutrinos in the early universe, ghostly particles that have since vanished. Or it might reveal that neutrinos interacted with something we have not yet dreamed of, an exotic force or a hidden particle that left its fingerprint on this ancient chill. This temperature tango is a delicate one. A single, precise measurement could either confirm our entire understanding of the universe's infancy or tear the textbook chapter on its first second completely in half. What other secrets are frozen into that near absolute zero temperature, waiting for a device sensitive enough to read them? That exact temperature reading holds a secret far deeper than just a head count of ancient particles. It is a direct line to one of the most puzzling questions in modern physics, the conundrum of neutrino mass. For decades, the standard model of particle physics, our most successful theory of the fundamental forces, insisted that neutrinos were massless, simple cosmic ghosts. Then experiments proved that was wrong. Neutrinos do have mass, a discovery so revolutionary it earned a Nobel Prize. But here is the haunting part: we still do not know how much. Our current methods can only measure the tiny differences in mass between the 3 neutrino types or flavors. It is like knowing one sibling is slightly heavier than another, but having no idea what any of them actually weigh. This is where the cosmic neutrino background becomes a cosmic scale. The precise way these ancient neutrinos clumped together in the early universe, a pattern imprinted on the large-scale structure of everything we see today, is exquisitely sensitive to the absolute mass of the lightest neutrino. A heavier neutrino would have smoothed out the cosmos in a subtly different way than a lighter one. By studying the faint gravitational fingerprint left by the CNB on galaxies and clusters, we could finally weigh the lightest known particle in the universe. Knowing this single number would be a monumental breakthrough. It would shatter the standard model, forcing a complete rewrite of our understanding of matter's most basic building blocks. It would also tell us how much these ghostly particles contribute to the total mass of the cosmos, locking in their role in the story of dark matter and the ultimate fate of the universe. The answer to what seems like a tiny, technical question, what does the lightest neutrino weigh, could reshape our entire conception of reality. But the ghostly imprint of these particles might hold the answer to an even deeper cosmic imbalance. Why does anything exist at all? Every particle of matter we know, from the atoms in our bodies to the most distant stars, should have been annihilated by an equal amount of antimatter in the universe's first moments. Yet here we are in a cosmos dominated by matter. This is the great matter-antimatter asymmetry problem, and the cosmic neutrino background could be hiding a crucial part of the solution. Physicists call this the lepton asymmetry enigma. Leptons are the family of particles that include electrons and, most importantly, neutrinos. We suspect that for the universe to have the matter we see today, there must have been a fundamental imbalance not just for quarks, the building blocks of protons and neutrons, but for leptons as well. A slight primordial preference for neutrinos over antineutrinos in the first second of time could have been the seed that tipped the entire cosmic scale. The CNB is the fossilized record of that potential imbalance. If the early cosmos held even a tiny fraction more neutrinos than antineutrinos, that signature would be forever frozen into the properties of the relic neutrino we are trying to detect today. It would subtly change how the particles are distributed and how they behaved in the ancient cosmic soup. Finding that signature would be like discovering the first domino that fell in a chain reaction leading to our very existence. It would confirm that the laws of physics themselves are slightly skewed in favor of creation over annihilation. This is not just a minor detail. It is a fundamental question about why the universe is habitable. A confirmed lepton asymmetry in the cosmic neutrino background would provide the missing piece to one of the greatest puzzles in science, revealing why there is something rather than nothing. What other primordial secrets about the birth of our material world are encoded in that silent, ghostly sea? This question of existence leads directly to a cosmic hide-and-seek game happening right here in our own galaxy. Are these ancient neutrinos spread evenly throughout the universe like a thin, uniform fog, or have they been subtly gathered by gravity, forming a denser halo around colossal structures like the Milky Way? This is the relic neutrino clustering puzzle, and the answer would reshape our understanding of gravity on the largest scales. For the longest time, physicists assumed these ghostly particles were too fast, too energetic to be captured by anything. They would stream freely, creating that perfect diffuse sea. But our revised understanding of neutrino mass changes everything. If neutrinos have even a tiny amount of mass, and we know they do, then they must feel the pull of gravity. Over billions of years, the immense gravitational wells of galaxy clusters and dark matter halos could have slowly concentrated these particles, pulling them into a slightly thicker swarm around the most massive objects in the cosmos. Imagine a vast, invisible atmosphere clinging to our galaxy, a ghostly aura made of the oldest particles in existence. Detecting this clustering would be a direct measurement of gravity's patient work on the most elusive substance. It would show us how the largest structures in the universe, woven from both dark and visible matter, have sculpted the primordial neutrino background. If we found a dense halo, it would give us a powerful new tool. By mapping how these relic neutrinos are distributed, we could essentially use them as tracers to chart the invisible dark matter scaffolding that holds galaxies together. We would be seeing the dark matter not directly, but by watching how it has gathered the universe's oldest ghosts. Yet if they remain a uniform fog, it implies something just as profound, that their intrinsic properties make them immune to even the strongest gravitational pulls. Either outcome forces us to confront the fundamental nature of these particles and the gravitational forces that have been shaping them since the beginning of time. The silent halo holds a map to the cosmos's dark skeleton, waiting to be read. This silent halo of ancient neutrinos might be doing more than just mapping the darkness. It could be actively talking to it. One of the most profound mysteries the CNB might help solve is the true identity of dark matter itself. We know dark matter exists because of its gravitational pull, but we have no idea what it is made of. What if the answer lies in how it interacts with the oldest particles in the universe? Consider a startling possibility. Could dark matter particles be constantly scattering off these relic neutrinos? Think of a vast, invisible dance happening all around you. Billions of dark matter particles, themselves utterly elusive, might be occasionally bumping into the even more ancient ghost particles from the Big Bang. While neither participant can be seen directly, their cosmic waltz would leave footprints everywhere. Every such interaction, every tiny scatter, would steal a minuscule amount of energy from the dark matter. Over the eons, this would have a slowing, cooling effect on the entire dark matter population. This cooling would fundamentally change how dark matter clumps together to form the gravitational scaffolding for galaxies. If dark matter is too fast and hot, it would smooth out and prevent small galaxies from forming. If it is colder and slower, it clumps more easily, matching what we actually observe in the universe. The cosmic neutrino background could have been the universe's original cooling system for dark matter. By studying the precise distribution of galaxies in the sky, we are indirectly measuring how cold the dark matter is. That measurement, in turn, points back to whether it was chilled by constant, subtle collisions with a sea of relic neutrinos. This gives us a completely new way to probe the dark sector. We would not be trying to catch a single dark matter particle in a lab. Instead, we would be reading the collective story of how all dark matter has behaved across cosmic time, a story written in part by its ancient dialogue with the CNB. Finding evidence for this interaction would be a monumental breakthrough. It would not only confirm that dark matter is a real particle, but it would also tell us something about how it communicates with the rest of the cosmic reality, even if only through the gentlest of touches with the universe's oldest ghosts. What other invisible conversations are happening in the void, conversations that shaped the very structure of our cosmos? These invisible conversations between dark matter and neutrinos are not the only whispers from the dawn of time. Another, even more fundamental force may have left its mark on this ghostly sea. The very fabric of the newborn universe might have been threaded with immense primordial magnetic fields. We know magnetic fields exist today, woven through galaxies and the vast spaces between them, but their origin is a profound mystery. Did they form later around the first stars, or were they born in the unimaginable violence of the universe's first instance? The cosmic neutrino background could hold the answer. If these colossal magnetic fields existed when the CNB was formed, they would have done something remarkable to the fleeing neutrinos. They would have polarized them. Think of polarization as making all the particles vibrate or spin in a preferred direction, like aligning countless tiny compass needles. We have already seen this with light. The cosmic microwave background, the first light, carries a faint polarization pattern, a fossilized imprint of those first magnetic fields. But light was set free hundreds of thousands of years after the Big Bang. Neutrinos decoupled after just 1 second. If we could detect a polarization in the cosmic neutrino background, it would be a snapshot of magnetic fields from a time 1,000,000 times earlier than the CMB can show us. It would be like finding a document written in the universe's first breath rather than its first coherent sentence. This would revolutionize our understanding of cosmic magnetism. It would prove that magnetic fields are not a later cosmic addition, but a foundational feature of reality woven into the cosmos at its birth. The hunt for this polarized signal is a hunt for the universe's very first force fields, a signature of dynamics so ancient we can barely conceive of them. What turbulent energies in that first second could have forged magnetic fields strong enough to align the ghosts of creation themselves? Those first magnetic fields would have existed alongside another, even more fundamental cosmic vibration. Before there was light, before there were atoms, the infant universe was filled with sound. Not sound as we know it, traveling through air, but colossal pressure waves rippling through the seething, dense plasma of creation. These are the primordial acoustic oscillations, the literal sound of the Big Bang itself, and their echo is frozen into the cosmic neutrino background. In the first few minutes, the universe was a chaotic, boiling soup where particles of light, or photons, were locked in a constant tug of war with the force of gravity. Gravity would try to pull matter together into clumps, while the intense radiation pressure of the photons would push it back out, creating a rhythmic pulse. This push and pull set the entire cosmos ringing like a bell. These sound waves traveled at an incredible speed, a significant fraction of the speed of light, and they left their mark on everything, including the neutrinos that were about to flee the scene. As the neutrinos decoupled and streamed freely, they carried with them a snapshot of these vibrations. The pattern is subtle but incredibly specific, a preferred scale imprinted on how these ghostly particles are distributed in space. It is a fossilized recording of the universe's earliest rhythm. Unraveling this pattern from the CNB would be like finding a perfect, high-fidelity recording of the Big Bang's first notes. This is not just a cosmic curiosity. The properties of these sound waves are exquisitely sensitive to the exact ingredients of the early universe. The rate at which they traveled, the distance they could cover before fading, all of it depended on the precise mix of ordinary matter, dark matter, radiation, and dark energy. By measuring the detailed pattern in the neutrino background, we could read off a recipe for the cosmos from a time before the first stars or galaxies even had a chance to form. It would give us an ultra-high-precision record of the universe's composition and expansion rate in its first few minutes, a window into an epoch we can currently only theorize about. This sonic fossil could confirm or completely rewrite our understanding of what the universe was made of at its very beginning, all by listening to the silent vibrations captured by its oldest ghosts. This cosmic soundscape of the early universe is built on a profound assumption that the neutrinos we are trying to detect are still there, but what if they are not? This leads us to a deeply unsettling possibility, the neutrino decay dilemma. Our standard models treat neutrinos as essentially stable, eternal ghosts that have traveled for over 13 billion years unchanged. Yet many compelling theories that reach beyond our current physics suggest they might not be immortal. Neutrinos could be slowly, imperceptibly decaying into something even more elusive. Imagine a particle so ghostly it fades into something even less substantial. If neutrinos decay, they would transform into particles we have not yet discovered, perhaps a lighter, sterile neutrino or even a wisp of dark matter. This process would be unimaginably slow, taking trillions of years for a single particle to transform, but the universe has had billions of years to work. A decay rate that seems negligible on human timescales could have a cumulative, dramatic effect on the cosmic neutrino background we hope to observe today. The most immediate consequence would be a ghostly thinning of the cosmic sea. The predicted density of relic neutrinos, the number that should be flowing through every cubic centimeter of space, would be lower than our calculations suggest. They would have been quietly disappearing one by one across cosmic time. Even more telling would be a distortion in their energy spectrum. Heavier neutrinos would decay first, leaving behind a population that is skewed toward the lighter end. Trying to detect the CNB and finding it is fainter or has a different energy profile than expected would be a direct, if haunting, signature of this decay process. This is why the hunt for the cosmic neutrino background is about so much more than just finding an ancient relic. It is a direct test for the ultimate stability of matter. Confirming decay would be a monumental crack in the standard model of particle physics, forcing us to completely rethink the lifespan of the universe's most abundant particles. It would open a portal to a hidden sector of reality, revealing new laws and new particles that govern the most fundamental decays. The silence we hear when we listen for these ghosts might not be emptiness, but the quiet sound of them vanishing into something else entirely. While we listen for the silent decay of these ancient particles, we must also ask what other primordial secrets they have perfectly preserved. The cosmic neutrino background offers a potential window into an era even more remote than its own birth, the very first fraction of a second of the universe. This is the mystery of the cosmic inflation imprint. According to our best theories, the universe underwent an unimaginably violent growth spurt called inflation, expanding faster than the speed of light for a fleeting moment right after the Big Bang. This event set the stage for everything to come, and it is believed to have generated ripples in the very fabric of spacetime itself, known as primordial gravitational waves. We have been searching for the faint echo of these waves for decades. The cosmic microwave background, our previous oldest relic, does show hints of their influence, but it is a muddled signal. That first light was set free 380,000 years after the Big Bang, a cosmic eternity during which the pristine waves from inflation were scrambled and distorted by the turbulent plasma of the young cosmos. The CNB, however, decoupled after only one single second. It escaped the chaos almost immediately. This means the neutrino background was never buffeted or altered by the dense soup of particles that clouded the universe for its next several 100,000 years. It carries a signal that is potentially 1,000,000 times cleaner and more direct. If primordial gravitational waves from inflation did indeed ripple through the universe in that first second, they would have left a distinct twisting pattern on the escaping neutrinos, a specific type of polarization. Finding that signature in the cosmic neutrino background would be the ultimate archaeological discovery. It would be like finding an unopened scroll from the universe's very first moment, while the CMB is a copy of a copy made much later. This would not merely confirm that inflation happened, it would tell us its exact energy scale and what drove it, revealing the physics of the universe at energies so high we could never hope to recreate them in a laboratory. The silent sea of relic neutrinos is not just a fossil, it is a time capsule from the very edge of time, holding a whisper of the cosmos's first and most dramatic birth cry. What other fundamental truths about creation are locked within that unpolluted signal, waiting for us to learn how to listen? But this pristine time capsule might also be concealing a phantom. The hunt for the cosmic neutrino background is intertwined with the search for something even more ghostly, a sterile neutrino. This is not merely a fourth type of neutrino, it is a hypothetical particle that refuses to play by any of the known rules of physics. Unlike the three active neutrinos we know, which at least interact through the feeble, weak nuclear force, a sterile neutrino would be utterly aloof. It would feel only gravity, ignoring every other force in the universe. This makes it a perfect candidate for a component of dark matter, but it also makes it nearly impossible to detect directly in any experiment on Earth. How could we possibly find a particle that does not interact with anything? The answer lies in the ancient history of the cosmic neutrino background. In the first second, the universe was so dense and hot that even these sterile phantoms could have been born. More importantly, the three active neutrinos we know could have oscillated or morphed into these sterile states and back again. This cosmic flavor swapping would have been a constant, frantic dance in the primordial soup. This dance would have left a permanent scar on the relic sea. The precise ratio of electron neutrinos to muon neutrinos to tau neutrinos frozen into the cosmic neutrino background is a direct record of those early oscillations. If sterile neutrinos were part of the mix, they would have stolen energy and altered the rhythm of this dance. The final flavor composition of the relic neutrinos we hope to detect would bear a distinct, calculable mark of this phantom partner. It would be a specific, telltale skew in the population, a signature that standard physics with only 3 neutrinos cannot explain. Finding that skew would be the ultimate smoking gun. We would not be detecting the sterile neutrino itself. We would be reading the shadow it cast upon its cosmic cousins over 13 billion years ago. It would be proof of a completely new fundamental particle, a hidden actor that has been shaping the universe from the shadows since the very beginning. The silence of the CNB could be broken by the echo of a ghost we have never seen, a specter whose only evidence is the subtle wound it left on the oldest particles in existence. This silent sea of ancient neutrinos might hold the key to a modern crisis shaking the very foundations of cosmology. Right now, scientists are locked in a fierce debate over a single, crucial number, the Hubble Constant, which measures how fast the universe is expanding today. The problem is stark. 2 of our most trusted methods are giving us 2 different answers. One method, using the cosmic microwave background as a fossil from the deep past, gives a slower, more sedate expansion rate. The other, measuring the distances to exploding stars in the nearby universe, gives a faster, more frantic one. This is the Hubble constant tension, and it is more than just a statistical fluke. It suggests that our entire understanding of cosmic history might have a fundamental crack in it. Either one group has a hidden error in their measurements, or the universe itself is doing something our models do not predict. This is where the cosmic neutrino background enters as the ultimate independent referee. Because these relic neutrinos were set free just 1 second after the Big Bang, their properties are a direct record of the universe's expansion history from that very first moment to the present day. Think of the CNB as a cosmic tape measure that has been stretching for 13.8 billion years. A precise detection of its temperature and how its particles are distributed would give us a third, completely independent way to calculate the Hubble constant. This measurement would not rely on the physics of ancient light or the behavior of modern stars. It would come from the ghostly echo of the primordial soup itself. If this new, third measurement agrees with one of the existing values, it would likely settle the argument, telling us which path to trust. But if it gives a third, entirely different number, the implications would be truly revolutionary. It would be a clear signal that we are missing a major ingredient in our cosmic recipe, perhaps a new type of dark energy that flickered on and off, or a strange property of neutrinos we have never imagined. The silent whisper of the CNB could either calm the waters of modern cosmology or plunge us into a deeper, more exciting mystery, forcing a complete rewrite of the universe's life story. This long journey through cosmic time makes relic neutrinos the ultimate test subjects for the fabric of reality itself. Their 13 billion-year voyage could reveal if space-time is not the smooth continuum we imagine, but a seething, chaotic foam at the smallest possible scales. This is the frontier of quantum gravity, the quest to unite Einstein's theory of gravity with the quantum world. The problem is that this quantum foam, if it exists, would operate on a scale so vanishingly small, 1 trillion times smaller than a proton, that no experiment on Earth could ever hope to see it directly. But the universe provides its own laboratory. Over a journey spanning billions of light years, these tiny, frothy imperfections in spacetime would act like cosmic cobblestones. A neutrino traveling such an immense distance would not glide on a perfectly smooth surface. It would jitter and vibrate, its path ever so slightly randomized by the foam. Think of it like light from a distant star. As that light travels through our turbulent atmosphere, it twinkles. The quantum foam of spacetime would cause a similar effect, but for particles, not light, and over the entire history of the universe. For most particles, this effect is negligible, but the cosmic neutrino background is unique. These particles have traveled the longest possible distance at the lowest possible energies, making them exquisitely sensitive to the subtlest of road bumps. A high-energy photon from a gamma-ray burst might barrel over the foam without noticing. A low-energy relic neutrino, in contrast, would feel every single bump and ripple across its epic journey. By the time these ancient ghosts reach us, their properties could carry a faint, fossilized imprint of that turbulent spacetime texture. If we can decode that imprint from the CNB, it would be our first direct evidence of quantum gravity in action. It would prove that spacetime itself has a granular, pixelated structure when viewed at the fundamental level, a revolutionary discovery that would reshape our understanding of existence. The silent sea of neutrinos is not just a relic of the past, it is a billion-year-long experiment testing the very nature of space and time. What other fundamental textures of reality have these cosmic travelers recorded on their endless journey? This fundamental identity crisis touches the very nature of the neutrino itself. Are these ghostly particles unique in all of creation? The question is whether a neutrino is its own antiparticle. In the particle zoo, most matter particles have a distinct antimatter twin. An electron has a positron, a proton has an antiproton. These are called Dirac particles following one set of rules. But a fascinating possibility proposed by the physicist Eta Majorana suggests that for truly neutral, chargeless particles like the neutrino, this twin might not exist at all. A Majorana neutrino would be its own antimatter counterpart. It would be a perfect cosmic palindrome, identical to its own mirror image. If this is true, the implications are staggering. It would mean that the faint sea of the cosmic neutrino background is not actually a mix of two different things, neutrinos and antineutrinos. Instead, it is a uniform ocean of a single, self-contained entity. The very labels we use would lose their meaning. This is not just a philosophical curiosity. The Majorana nature of neutrinos is considered a possible gateway to understanding why the universe has more matter than antimatter. A key process called neutrinoless double beta decay, which can only happen if neutrinos are their own antiparticles, could have tipped the cosmic scales in our favor. While experiments deep underground are hunting for signs of this rare decay, the cosmic neutrino background offers a completely different line of evidence. If neutrinos are Dirac, the relic sea has a specific, predicted mix of particles and antiparticles. But if they are Majorana, the overall properties of this background would be subtly different. Its collective behavior, how it influenced the formation of the very first structures in the universe, could bear the imprint of this profound self-identity. Detecting the CNB and carefully measuring its statistical properties could, in principle, reveal this fundamental truth. We would be reading the answer to a deep particle physics question, not in a giant accelerator, but in the gravitational whisper of the oldest particles in existence. The ghost sea holds the key to whether the neutrino is a lone wolf, a particle that needs no other, or just one half of a pair lost in time. The violent expansion of cosmic inflation could not last forever. When it ended, the universe did not simply calm down, it underwent a spectacular transformation known as reheating. In a phenomenal release of pent-up energy, the same field that drove the universe's frantic growth decayed, flooding the empty cosmos with a hot, dense soup of particles and radiation. It was in this explosive moment, this cosmic rebirth into a seething reality of matter and force, that the very first neutrinos were forged. The cosmic neutrino background is a direct relic of that reheating era, a snapshot of the universe's first tangible breath after its abstract birth. And this is where a profound mystery takes root. The specific way inflation ended and reheating began is one of the greatest unknowns in cosmology. Did it happen suddenly, like a dam bursting, or was it a slow, sputtering process? Did the inflattened field, as it is called, decay smoothly or through violent, resonant oscillations? The answers are not just academic, they determine the initial conditions for everything that followed, from the formation of the first atomic nuclei to the birth of galaxies. The detailed energy spectrum of the cosmic neutrino background could be the only record of this pivotal event. As the neutrinos decoupled and streamed free in that first second, they locked in a precise distribution of energies, a fingerprint of the thermal state of the universe at the exact moment of their birth. This energy spectrum is not just a simple curve. It could contain subtle bumps and wiggles, imprints of the specific resonant frequencies at which the inflattened field shook itself apart. It would be like finding the unique vibration pattern of the bell that rang at the dawn of time. Different models of reheating predict different spectral fingerprints. A violent, resonant decay would produce a spectrum rich with specific features, while a slow, smooth transition would result in a much cleaner thermal distribution. By one day measuring this spectrum with exquisite precision, we would not just be detecting ancient particles, we would be reading the engineering schematics of the universe's ignition sequence. This ghostly sea holds the only known witness statement to the end of inflation and the fiery beginning of the hot Big Bang universe we call home. What turbulent physics forged our reality in that first unimaginable flash, and is its unique signature still carried by the oldest travelers in the cosmos? This primordial conversation among neutrinos themselves is another layer of the mystery. We assume these particles are the ultimate loners, ghosting past each other without a word. But what if in that first, frantic second, they were actually chatting constantly? The standard model of particle physics insists that neutrino interactions are vanishingly weak, a fleeting whisper. Yet several compelling theories suggest that in the extreme energies of the newborn cosmos, neutrinos might have had a much stronger voice, engaging in frequent collisions with one another. This is the puzzle of neutrino self-interaction. If true, the cosmic neutrino background would not have been a thin gas of independent particles all flying off on their own. Instead, it would have behaved like a cohesive fluid, a dense, swirling ocean where each neutrino was in constant contact with its trillions of neighbors. Think of the difference between a crowd of people all silently walking in straight lines, never touching, versus a packed dance floor where everyone is moving together, influencing each other's direction and rhythm. A free streaming gas of neutrinos would have poured out of dense regions in the early universe, smoothing them out and suppressing the growth of the very smallest cosmic structures. But a fluid, a self-interacting sea, would have had viscosity. It would have clung together, resisting that rapid dispersal. It would have stayed in place longer, acting as a gravitational anchor that allowed tiny clumps of dark matter to coalesce more easily. The signature of this ancient social behavior is frozen into the large-scale structure of the universe we see today. By mapping the distribution of the smallest, faintest dwarf galaxies and the faintest wisps of intergalactic gas, we are indirectly charting the ghostly influence of that first neutrino sea. If we find an overabundance of these small-scale structures, it could be the fossilized evidence that neutrinos were not loners after all, but a deeply interconnected collective. This would shatter a key prediction of the Standard Model, forcing us to rewrite the rules of engagement for the universe's most elusive particles. The silent background we seek may not be silent because its constituents were always alone, but because their intense early conversation ended long ago, leaving only its structural echo imprinted across the cosmos. This invisible architecture of dark matter and neutrinos is built upon a foundation of ordinary stuff, the very atoms that make up you, me, and every star we can see. Yet cosmologists face a baffling inventory problem. When we count up all the normal matter, or baryons, in the present-day universe, from galaxies to gas clouds, a huge portion is simply missing. Based on the pristine recipe cooked up in the first few minutes during Big Bang nucleosynthesis, we know exactly how much ordinary matter the universe should contain. But our telescopes can only find about half of it. So where did the rest go? The missing baryons are not lost to some other dimension. They are believed to be hiding in a form almost impossible to see, a tenuous, superheated gas strewn through the vast filaments of the cosmic web. This gas is so hot it emits very little light, and so diffuse it escapes direct detection, creating a ghostly halo of normal matter around the entire universe. This is where the cosmic neutrino background, in its silent omnipresence, could become an unlikely guide. If the relic neutrino sea is not perfectly uniform, if it has been gathered into those dense halos around galaxies and clusters as we discussed, then its collective gravitational pull is not zero. It exerts a subtle, persistent tug. Over billions of years, this ghostly gravity would have gently shepherded the invisible, hot baryonic gas, coaxing it to follow the same invisible trails. The denser the neutrino background in a region, the more it would have concentrated that hidden, ordinary matter. We cannot see the neutrinos directly, and we struggle to see the hot gas, but we can see their combined gravitational effect. By meticulously mapping the slight distortions in the cosmic microwave background as it passes through these large-scale structures, a technique known as the kinematic Sunyaev-Zeldovich effect, we are essentially taking an X-ray of the cosmos. The patterns we see reveal the pressure and distribution of this elusive hot gas. If that distribution perfectly aligns with the predicted gravitational map of a clustered cosmic neutrino background, it would be the ultimate confirmation. We would have used the oldest ghosts in the universe to finally illuminate the missing atoms of reality. Finding these baryons would solve a fundamental cosmic accounting error and complete our inventory of the normal matter that everything is built from. It means the universe has been hiding its most basic components in plain sight, using the faint gravity of its oldest particles as the only clue to their location. That 1 second mark is a threshold unlike any other in cosmic history. It is the moment the universe grew up, transitioning from a seething, opaque fireball into a place where ghostly particles could finally roam free. This is the epoch of neutrino decoupling, and the mystery is not just that it happened, but exactly how it unfolded. Was it a clean, instantaneous break, like a single snap of the fingers? Or was it a slow, messy divorce from the primordial plasma, a drawn-out farewell over many milliseconds? The difference is critical, for the precise nature of this separation is permanently encoded in the cosmic neutrino background itself. Before this moment, the universe was so dense that neutrinos were trapped. They would travel a tiny distance before smashing into an electron or a positron, constantly swapping energy and direction, trapped in the thick cosmic soup. But as the universe expanded and cooled, the average distance a neutrino could travel before a collision grew longer and longer. There is a specific point where this distance finally became greater than the entire observable universe at that time. At that instant, the neutrinos were effectively set free. They stopped being active participants in the thermal dance and became silent observers, their properties frozen in time. If this transition was perfectly sharp and instantaneous, the energy spectrum of the relic neutrinos would have a specific, pristine thermal shape, what physicists call a perfect Fermi-Dirac distribution. But if the decoupling was gradual, if some neutrinos escaped early while others lingered in a few final interactions, that perfect spectrum would be subtly distorted. The earliest escapees would have been slightly cooler, while the last to leave would have been a touch warmer, having stolen a little extra energy from the plasma in their final collisions. This would leave a faint but calculable wiggle in the energy curve of the entire cosmic neutrino background. Detecting that wiggle would be like finding the fossilized footprints of the very last steps these particles took before beginning their 13 billion-year journey. It would tell us the exact temperature and density of the universe during its first second with incredible precision. We could read the thermodynamics of the infant cosmos directly from this ghostly imprint. This is not just a detail about neutrinos, it is a fundamental test of how matter and energy behaved under the most extreme conditions imaginable. The silence of the CNB is not empty, it is a detailed logbook from the universe's first and most dramatic escape. What other secrets about that primordial chaos are written in the subtle distortions of that ancient energy spectrum? This alignment, nicknamed the axis of evil, is a deep and unsettling puzzle. It suggests that the universe's vast structure might have a preferred direction, a cosmic tilt that should not exist. The cosmological principle, the bedrock of modern cosmology, states that the universe is homogeneous and isotropic. It should look the same in every direction with no special place and no central axis. The axis of evil, if real, shatters that foundational idea. It implies we might be living in a universe with a fundamental lopsidedness, a preferred geometry written into the fabric of space at the largest scales. But is this a real feature or just a ghost in our data? The cosmic microwave background, for all its power, is a snapshot from a single cosmic epoch, 380,000 years after the Big Bang. It is like trying to understand the entire history of a forest by looking at a single photograph taken on one autumn day. The cosmic neutrino background, however, offers a way to take a second, independent photograph from a completely different time. These ghostly particles carry a snapshot of the universe from its first second of existence. If the axis of evil is a real feature of the cosmos, a genuine crack in the cosmological principle, then it must have been imprinted at the very beginning. It would be a property of the universe's initial conditions, a fundamental asymmetry woven into the inflationary expansion itself. In that case, the cosmic neutrino background should show its own version of this alignment, a correlated axis frozen into the distribution and motion of these ancient particles. Finding a matching axis in the CNB would be one of the most profound discoveries in the history of science. It would force us to admit that the universe has a grand architecture, a hidden spine that defines its large-scale structure. We would have to rewrite our textbooks, replacing the idea of a perfectly uniform cosmos with one that has a subtle, fundamental directionality. Conversely, if we could one day map the cosmic neutrino background and find it is perfectly isotropic with no trace of the axis of evil, the mystery would only deepen. It would suggest the anomaly is not a feature of the universe's birth, but something that happened later. Perhaps it was a local disturbance, a gravitational echo from something immense beyond our observable horizon, an imprint that only affected the later released photons of the CMB. The silent sea of neutrinos, the universe's first messengers, holds the key to distinguishing between a cosmic mirage and a true revolution. Their unimpeachable testimony could either confirm our deepest fears about an anomalous cosmos or restore our faith in a perfectly symmetric universe. Which version of reality do these ancient ghosts support? This chemical potential is a hidden dial on the cosmic control panel, a number that measures a fundamental imbalance in the ghost sea. In the simplest terms, it quantifies whether there were more neutrinos than antineutrinos in that first second. A value of 0 would mean a perfectly symmetrical universe, an equal number of particles and their mirror opposites. But a non-zero value, even a tiny one, would signal a primordial preference, a built-in bias for matter over antimatter from the very start. This is not a minor detail, it is a fundamental question about the universe's initial symmetry. Was the cosmos born perfectly even-handed, or was it always slightly tilted in favor of existence? The consequences of even a minuscule chemical potential are staggering. Let us rewind to the first few minutes, to the epoch of Big Bang nucleosynthesis when the first atomic nuclei were forged. The universe was a nuclear fusion reactor, and neutrinos were key players in the reactions that built hydrogen and helium. The density and energy of the neutrino sea directly influenced the rate of these reactions. If there was a chemical potential, an overabundance of neutrinos over antineutrinos, it would have thrown a wrench into this delicate process. Think of it like trying to bake a precise cake while someone is subtly adjusting the oven temperature. A higher density of neutrinos would have shifted the balance, altering the final amounts of primordial hydrogen, helium, and deuterium that we observe today. We can measure these ancient abundances with remarkable accuracy by looking at the oldest clouds of gas in the universe. Any significant deviation from the predictions of a perfectly symmetrical neutrino sea would be a direct fingerprint of that non-zero chemical potential. It would mean the lepton asymmetry we discussed earlier was not just a possibility, but a concrete, measurable feature of creation. The ghost sea would carry that initial bias frozen into its very being, affecting not only the past but also its present-day properties, like how its particles cluster under gravity. Constraining this number is one of the most important goals in cosmology. Finding it is zero would be a profound discovery, confirming a deep symmetry at the heart of the Big Bang. But finding it is not zero would be even more revolutionary, forcing us to ask what fundamental law could have written a preference for matter into the universe's first line of code. Our ancient neutrino sea is not a static relic but a dynamic, churning ocean. Each of these ghostly particles has been on an epic journey, and during that journey they have not remained the same. Neutrinos are cosmic shape-shifters, perpetually oscillating between their three identities, the electron, muon, and tau flavors. This means the cosmic neutrino background is not just a fossil, it is the universe's largest and most ancient natural oscilloscope. An oscilloscope is a device that measures changing waves, and over billions of light years, the CNB has been recording the most subtle of cosmic influences on its endless oscillation rhythm. The mystery is what has left its mark on this grand scale. Vast, intergalactic magnetic fields stretching between galaxies could have twisted the quantum properties of these neutrinos, subtly altering their oscillation probabilities. Even more profound is the persistent whisper of gravity. Every time a relic neutrino passed near a galaxy or drifted through an immense halo of dark matter, the sheer gravitational potential, the warping of space itself, could have minutely shifted its phase, nudging its flavor transformation. Over such incomprehensible distances, these tiny nudges would have added up, creating a complex, layered history written in the flavor composition of the ghost sea arriving at Earth today. Decoding this signal would be like reading a billion-year-long travel log. The final mix of electron, muon, and tau neutrinos in the CNB would not be random. It would be a precise record of the magnetic and gravitational landscape of the entire cosmos. By untangling this pattern, we could map the invisible magnetic fields that weave through the cosmic voids and chart the distribution of dark matter in a way no telescope ever could. We would be using the universe's oldest particles as sensitive probes to trace the architecture of everything they have passed through. This turns the cosmic neutrino background into a storybook, and each neutrino is a page describing the hidden terrain of the cosmos. What grand gravitational landmarks and phantom magnetic currents have these eternal travelers recorded on their way to us? This cosmic oscillation record leads us to a frontier beyond our familiar three-dimensional space. The silent sea of relic neutrinos might hold the key to proving the existence of realms we cannot see, extra dimensions of space predicted by string theory. Our universe might be a vast, multidimensional tapestry, with our reality confined to just a three-dimensional slice or brain floating within a higher dimensional bulk. In such a cosmos, the fundamental forces behave differently. While particles of matter and light might be stuck to our brain, gravity, the weakest force, could be unique. It might be able to leak, In the extreme energies of the first second, gravity could have seeped out of our dimensional plane and into these hidden extra dimensions. This gravitational leakage would have had a profound and immediate effect on the infant universe, dramatically altering how it expanded and cooled. The cosmic oven would have lost heat faster than expected because energy was draining into these unseen realms. This accelerated cooling would have directly impacted the neutrino background. The moment of neutrino decoupling, that critical 1-second threshold, would have arrived earlier. The temperature at which it happened would be different. The entire thermal history frozen into the CNB would bear the subtle, calculable signature of this early energy drain. If we can one day measure the cosmic neutrino background's properties with enough precision, its temperature and energy spectrum become a stringent test for these exotic theories. A perfect match with the predictions of a simple three-dimensional universe would place severe constraints on the size and number of extra dimensions, potentially ruling out entire classes of string theory models. But if the CNB data reveals a cooling curve that only makes sense if gravity was leaking away in that first second, it would be the first indirect evidence for a reality with more than 3 spatial dimensions. We would be using the faint thermal echo of the oldest particles to map the hidden geometry of all existence, proving that the cosmos is far grander and more layered than it appears. Yet the ultimate legacy of this ghost sea is written in the far future. Trillions of years from now, the cosmos will be a profoundly dark and lonely place. All stars will have long since burned out, their ashes scattered. Galaxies will have evaporated, their stars lost to the void. The universe will be a vast, expanding graveyard dominated by the ghosts of its past. In this final act, the cosmic neutrino background will undergo a stunning transformation. Today, its influence is dwarfed by dark energy and dark matter, a faint whisper in the cosmic chorus. But as the universe relentlessly expands and dilutes, the density of everything else will plummet. The neutrino sea, however, is everywhere, and its density, while incredibly low, is permanent. In that distant epoch, it will no longer be a background player. It will become one of the primary components of the entire cosmos, its collective gravity and pressure helping to steer the final rate of the universe's expansion. This is not a simple story. The role these ancient ghosts play depends entirely on the one property we are still trying to pin down: their mass. If neutrinos are extremely light, they will continue to behave almost like radiation, their pressure slowing the expansion in a particular way. But if they have a more substantial mass, even a tiny one, their behavior shifts. They become more like matter, and their collective gravitational pull will act as a subtle brake on the cosmos, a final, gentle tug from the oldest particles in existence. The precise value of that mass determines the final tension in the cosmic tug of war between expansion and gravity. It is a calculation that will play out over timescales we can barely comprehend, a final, quiet verdict on whether the universe expands into an ever colder silence or if the ghostly weight of its own history provides a small measure of closure. The fate of everything is connected to the mass of the lightest particle, a secret carried for trillions of years by a sea of ghosts from the first second of time. A revolutionary experiment is preparing to hunt the ghost. The PTOLEMY project, an acronym for the Princeton Tritium Observatory for Light, Early Universe Massive Neutrino Yield, represents one of the most audacious attempts to directly catch a relic neutrino. Its strategy is as brilliant as it is daunting. The plan is to coat a vast, ultra-cold surface with a thin layer of tritium, a rare and radioactive form of hydrogen. Here is where the magic happens. When a relic neutrino from the Big Bang flies through this surface, it has a minuscule but non-zero chance of striking a tritium nucleus. In that fleeting instant, the neutrino will be captured, transforming the tritium into a special, excited form of helium. This transformation would release a precise and unique jolt of energy, a signature that could, in theory, be detected. This signal would be the ultimate prize, the first direct confirmation that the ancient sea is real. The technical hurdles are almost beyond comprehension. The experiment must be shielded from the faintest background radiation, nestled deep underground to block cosmic rays. It must operate at temperatures near absolute zero to suppress any thermal noise that could mimic the signal. And it requires an unimaginable level of precision to measure that single, telltale burst of energy amidst a universe of random quantum fluctuations. Success would be an instant revolution. For the first time, we would not be inferring the ghost sea's existence from its gravitational shadow. We would be holding a piece of it in our hands, a direct sample from the first second of time. This would open the cosmic neutrino background to direct observational science, turning it from a theoretical ghost into a tangible cosmic specimen we can measure and analyze. The data flowing from such a detection would answer questions we have only dreamed of asking, revealing the exact mass, temperature, and density of this primordial sea, and instantly transforming our understanding of particle physics and cosmology. It would mark the moment we finally learned how to listen to the universe's oldest whisper. While we cannot yet hear its whisper directly, we can see its shadow moving across the cosmos. The ghostly sea of the cosmic neutrino background has left its signature everywhere, most clearly in the afterglow of creation itself, the cosmic microwave background. As the CMB radiation traveled for billions of years to reach us, the gravitational pull of all the matter in its path, including the vast, invisible ocean of relic neutrinos, subtly warped its journey. This creates two distinct, measurable imprints on the oldest light we can see. The first is on the CMB's angular power spectrum, the detailed blueprint of hot and cold spots across the sky. The presence of the neutrino background suppresses the formation of the very smallest of these spots. Think of it like a cosmic ghost trying to smooth out a rumpled sheet. The neutrinos, with their high speed and weak interactions, stream out of dense regions before gravity can fully clump matter there, washing out the finest details in the cosmic tapestry. The precise amount of this smoothing tells us the combined mass of all three neutrino species. The second imprint is even more direct through cosmic gravitational lensing. The collective gravity of the relic neutrino sea acts as a weak lens, bending the path of the CMB photons ever so slightly as they pass by. This distorts the pattern of the microwave background in a specific, calculable way, like looking at the universe through a faint, ghostly lens. By meticulously mapping this distortion, we can essentially chart the distribution of the neutrino background itself, weighing its gravitational influence across the cosmos. This is where our most powerful telescopes come in. Next-generation CMB experiments like the Simon's Observatory and the planned CMB-S4 are not just cameras for ancient light, they are neutrino detectors by proxy. With sensitivities orders of magnitude greater than their predecessors, they are measuring these subtle imprints with razor-sharp precision. Every new data point tightens the constraints on the neutrino's absolute mass, its potential interactions with dark matter, and the possibility of that primordial lepton asymmetry. They are using the light from the universe's infancy to illuminate the ghosts from its first second. These measurements are the threads that connect all 24 mysteries into a single, testable picture of reality. The silent sea may be invisible, but its gravitational echo is now ringing clear through our finest instruments, bringing us closer than ever to reading the secrets of the cosmic dawn. This faint whisper from the first second of time ties together the grandest puzzles of existence. From the ghostly identity of dark matter to the very reason anything exists at all, the cosmic neutrino background is a thread woven through the entire cosmic tapestry. It connects the infinitesimal world of particle physics to the vast architecture of the universe, challenging us to find a deeper set of laws. Our journey through these 25 mysteries reveals a single, profound truth. that the answers to our biggest questions are not lost in the past, but are flowing through us in a silent sea of ancient particles. The hunt for this ghostly signal is more than a technical challenge. It is a fundamental exploration of reality itself. As experiments like PTOLEMY push the boundaries of the possible, we stand on the verge of discoveries that could rewrite our understanding of everything. Stay curious, follow the progress, and listen closely for the echoes of creation. Which of these cosmic secrets would you most want to see unlocked?